somehow synchronize access to that database. And this is not enough. Software locks on each web server. That'll protect against that web server's clients, races amongst its own clients, but it will not protect against races between web servers. So we need something like this. Lock, like within SQL, then do all of our queries, then unlock. And what we saw to fix this was not a lock, but was a transaction with an extreme isolation level. So the idea of a transaction is, start it and then either commit or roll back. That does not mean lock and unlock. The main goal of a transaction is make sure everything gets within the transaction gets done. But with multiple transactions happening concurrently, they can interfere with each other, so we can specify how isolated do we want them to be. And with serializable, we saw that was enough to allow us to read something and then guarantee that after we have read it, its value won't change until our transaction is done. So we can do something like select in session 2, insert in session 1, try to select in session 2, and it gets delayed until session 1 commits. Okay. We can go the other way around. If I had already selected in session 2, then the insert in session 1 gets delayed. And if session 2 then ever does anything that would conflict with what session 1 is trying to do, one of them has to fail. Okay, so basically this kind of gives us, not really, but kind of gives us the same goal as what a lock would give us. Once I've selected some data, I know it's not going to change, and I can use that to make decisions and then change some rows based on those decisions without being interfered with. Okay, but a transaction is not a lock, and it's not intended to be used as a lock. They can solve some of the same problems as we saw. We were able to solve that, like, you have to leave one copy of any book for the library. So that necessitates doing a select, an if statement, then a possible insert. So SQL does actually provide locks. So we solved this problem with like a really strict transaction. We can also solve it with a lock. It has multiple ways, multiple locking mechanisms, and they do different things. And you have to kind of decide which one you need based on what you're doing. So it turns out you can actually just lock an entire table. And this is just like a mutex. Just say lock table, do whatever you want to do, unlock table. And then anyone else trying to use that table, depending on how strict your lock is, will either just have to wait or might be able to do some things as long as they don't interfere. And then we can actually just lock individual rows by using a select. So we can use a normal select syntax with an additional lock, and then if I only select, say, like 2 or 3 rows, then only those 2 or 3 rows get locked for other sessions. Question?
Just about the nature of the lock itself, like a mutex is used to lock a section. So for a table lock, is it actually locking all operations on the table?
So for a table lock, is it locking all operations on the table? Depends on what kind of lock. We'll see in just a second there are different kinds. But so actually, that's a good point. It is still not actually exactly like a mutex. It's not just like only one thread or process can be in here at a time. But it starts to look much, much more like a mutex. Okay, and the thing about select locks is they will be tied to a transaction. Table locks are not tied to a transaction. Select locks are. So the scope of a select lock is within whatever transaction it's running in. Okay, so let's look at table locks. You can just do SQL syntax, lock table, and then the table name, and then keyword read or write. So do you want to lock it for reading or do you want to lock it for writing? Those are kind of the different kinds of locks you can do. And then to unlock them, it's just unlock tables. We've been talking about transactions. Don't confuse this with a transaction. The lock followed by unlock, that does not imply that everything in there is a transaction. So you could still have server crash in the middle of this, and anything you've done up until that point will be committed. If you need a transaction, then you also need to use a transaction. The lock's not going to automatically do that. But if the server crashes while you hold a lock, it will automatically release that lock. So you can't just end up with complete deadlock forever. Okay, so if we lock a table for read, what this means, this kind of means different things based on which session you're in. Any session can still read from that table. So it's like the session you ran that's holding the lock can read. Any other session, even if they're not holding a lock, can read. Other sessions, if they try to write, will stall. Even if they don't use the lock and unlock syntax. If some table holds a read lock, if some session holds a read lock on the table, then no other session can write to it. The actual session that locked the table, instead of delaying on a write, will just fail on a write. You wouldn't want it to delay on a write because that would be guaranteed deadlock, because then it can't go and unlock. It will never be able to unlock the table. So it's treated as a syntax error. If the session holding a read lock tries to write, it just fails. If another session tries to write, then it stalls until the lock is released. So this basically lets you, it guarantees that while you're doing whatever you're doing, the state of the table will not change. You can read anything out of it, and you're guaranteed that it's static during that time. And then, so here's kind of the time diagram between two sessions. Session 1 locks. Session 2 does not. It could, actually. But both of them can select. These selects don't delay each other or anything like that. The session 2 trying to insert gets delayed because another session holds a read lock. Okay? And then lock table for write. So it's kind of just, it's a more strict for other sessions, less strict for the locking session. The locking session can now read and write, whereas with a read lock, even the locking session couldn't write. And then other sessions, even if they try to read, all they're trying to do is read, they will stall, or writing will stall. And then if they also try to acquire a lock, they will stall. So locking for write means you need exclusive access to the table. Like nobody else can even read because you are specifying that you're going to be changing stuff in there. Okay, so that should say write. So if session 1, come on PowerPoint, you can do it. Okay, so if session 1 holds a write lock, it can do inserts and selects, anything it wants, but it's guaranteed that it has exclusive access to that table. And then even trying to do a select in some other session will be delayed. So I've got my 2 sessions here again that I'm trying to fit on one screen. And I'm in the sandbox, so I just have 2 really simple tables. All I have is an int, and it's the primary key. The columns themselves is not what's interesting here. So if I do lock table T write. So I'm locking this table for writing. Okay, it says okay, I can select things out of it. Over here, I cannot even select. And I haven't even done anything yet. I haven't written anything, and still it's not letting me select until I unlock tables. Now this select can proceed. If it had been a write, then it would have also proceeded as soon as the lock was released, as long as whatever write it did didn't conflict with some write that I did while holding the lock. If it did, then it would just, the command would have failed. Okay, if I do lock table T for read, now I can select all I want. If I try to insert, it says, you can't do that. You've locked this for reading. That means you do not intend to do any writing. Over here, if I try to insert, it doesn't fail. It just stalls. Because this top session doesn't really, it shouldn't need to know that some other session might be holding a lock. So trying to insert shouldn't fail. It should just hold it up until I unlock tables. And then it's allowed to proceed. Okay? So, kind of same idea as these like highly isolated transactions. We get some of the same behavior where things wait until it's safe for them to proceed. Yeah.
Can you only unlock like everything at once?
Yeah, you can only unlock everything at once. Yep.
So why did it fail on insert?
Why did this one fail on insert?
Yeah.
Because I specified that I'm locking for read. So if I have locked for read, I'm specifying that I'm planning on using this in a read-only way. So it just, the rules are just you cannot insert while you hold a read lock.
So what's lock right? Lock right means
Lock write is where you're specifying that you need exclusive access to the table to read and write, potentially. And so that's why locking for write does allow me to insert.
So locking for write allows you to read and write.
Yep.
So what's the point of locking that table?
What's the point of locking the table?
Yeah, like what's the point of locking on write if you can read and write on that table?
What's the point of locking for write if it lets you read and write? Because it only lets this session read and write. It doesn't let other sessions read and write until the lock is released. Yeah.
Sorry, you said that you can only unlock everything at once. Can you not just hit unlock the table?
Say that again. You can
Can you not write unlock in to unlock this table you lock?
No, so you cannot do something like unlock T or unlock table T.
Meaning if you have two tables locked, you could lock in different operations. If one of them is unlocked, the other will unlock also.
Yes.
The other operation.
You have to write your queries in a way that everything is done when you unlock the tables. Yep.
So effectively, only one lock operation can be done at a time.
You can lock multiple tables at a time. You have to do everything you need to do before unlocking all of them. Yeah. Okay. So, question first.
Quick question. If you put a lock on read on a table, is that similar? Does like a normal select? If I was just going to select something from a query, does it put a lock on that table in the background so that maybe that table doesn't get anything written into it while I'm selecting from it? Is that just like something that like Mario DB does? Or
Right. If you select for read, the DBMS the database, the process that is actually the database server, will, it has some internals. It has its own locks, something like a mutex maybe. Or it's probably actually storing this actually in a table somewhere that prevents other sessions from doing anything with that table.
So you can always guarantee that when you're selecting some data, it's going to be at the moment you fire that select, that's the data you're going to get back, and it's not going to write anything in the process of it doing.
So if you hold a read lock and you select some data, you are guaranteed that whatever you selected is the static state of that data until you release the lock. Because the only thing other sessions are allowed to do is read on that table. Okay. So it turns out this is not a better way of solving the problem we solved last time, the checkout book problem where we need to make sure there's one copy left. And in fact, locking an entire table is actually pretty rare in practice. You only do this when you're making huge, major changes, like importing a database or exporting a database or completely changing the schema of some table. In your everyday queries that are just normal use of the database, you probably will never have a table lock because it's too extreme. It prevents any other query from messing with that table. So to show that, let me go back to my two sessions. And let me go back to set session, transaction isolation level, serializable. So this is what we were doing last time. Instead of locks, I'm going to use serializable transactions. Now over here, I'll start a transaction. And let's say I do delete from T where the int call value equals 1. So I'm going to delete this row from the table. But I'm doing it inside of a transaction. Okay. Over here, I'll start a transaction. And now I can do something like select star from T where int call equals 3. And it lets me do it. If I had locked, instead of a transaction, if I had done lock for write, then the entire table is locked. No other session can do anything. This would not work. The fact that I was deleting row 1 and selecting row 3, it knows that those don't conflict with each other, so it lets the read go ahead. That is a big and important difference between a full table lock and a serializable transaction. They can still run concurrently as long as they're not interfering with each other. I'm going to roll back both of those just to make sure I don't change any tables. Yeah.
Did you always still select row 1 in the second transaction before you commit the first one?
Okay, good questions. Would I be able to select row 1? So I did 3 instead of 1. Start a transaction again. Delete from T. Start a transaction and then select where row equals 1. And no. So this is where it's much smarter than a table lock. It's not going to let me break things, but it is going to let me proceed as long as it doesn't break things. This is a case where it would break things, so it has to stall. If I roll back now, then it lets the select proceed. If I commit, then the session on the top, that query would fail. Fail. Yep. Well, actually, now I'm not sure. Now I'm not certain. Let's try it. Best way to answer that question. Oh, it works actually. Okay. So it doesn't fail. It says 0 rows. Yeah. So so if I had tried to do 2 conflicting inserts, one of them would fail. Since this one is a delete, and it just says, all right, well, that row's gone, select something. So there's some cases it will fail, some cases it will work. Okay. Yes? So locks are uncommon. Should you use transactions all the time? The default in SQL is every single command you run is a single command transaction. You can turn that off. I'd recommend leaving it on. Should you use manual transactions all the time where you have complex statements? Only if it's important that it can't fail in the middle of the sequence of complex statements, like deducting from one bank account, adding to another bank account. Yep.
So when you lock on read, so other sessions cannot write to the table, but can you still write to the table?
When you lock on read, nobody can write to the table. Okay, so we could solve our library problem this way. Lock the entire checked out table, figure out how many books are left, if there are enough, insert into it, and then unlock tables. It has to be locked for write, since we are doing a write. But then any other query that's just trying to read from this table, or write to some completely unrelated row, would also be stalled unnecessarily. So let's look at select locks instead of locking the full table. They are usually in the context of a transaction. So start transaction, and then you do select whatever, normal select syntax, and then at the end, for update. So that means you are selecting a row with the intention of using that information to then go and update that row. Or update some other related row. And then you either commit or roll back, and that is what defines the scope of the lock. So as soon as you select it, it's locked. As soon as you commit or roll back, it's unlocked. And it only locks the rows that were related to the actual select. So you can do a where clause instead of just select everything, which would be like a table lock. You can select something where column equals 2 or whatever. And then it only locks that row. Other transactions can go and mess around with column 1 and column 3. And no problem, they don't interfere. So how do these kind of interact between sessions? Other sessions can do non-locking selects. So as long as they don't specify for update, they can select anything, even if some other session holds a lock on the row. They will stall if they try to do a locking read, and they will stall on any kind of write. And then the stall will stall until the transaction is rolled back or committed. Yeah.
So what if you specify on update but outside of the transaction?
So if you specify on update but outside of a transaction, that is actually in a transaction just for that single select command. So it'll lock it, select it, and then unlock it. It's kind of, yeah, it's, if you had a more complex query where you are actually changing things as well, then that would be useful.
Go back to the syntax on the previous slide real quick. So you don't actually like type lock anywhere.
Right. You don't say lock and unlock. You just say select for update. And then if this was the only command, then it would just lock it, run the select, and unlock it. But they're more useful in the context of a transaction, because then the scope of the lock is until the end of the transaction.
Oh, and then it'll automatically unlock?
Then it automatically unlocks. Yeah. So say I have session 1 and session 2 both running exactly the same transaction. So this is kind of like the library checkout transaction. They both start their transaction at the same time. They both try to do select for update at the same time. One of them succeeds. One of them will stall until the other transaction is committed. And so this is, just like, any two threads racing on some atomic updater. If they get there at the same time, one of them will proceed, one of them will wait. Okay, so select for update works essentially the same way as our serializable transaction does, where only the things that actually need to be locked are locked. The difference is it gives you control over, it lets you decide what needs to be locked instead of just everything. So you can say only these selects are for update. Some other select could just be, give it to me, I don't care if it changes. So that's essentially the difference between full serializable transaction and transaction with select for update. So you can turn the isolation level down to like repeatable read or even lower, and select for update will still work. It'll stall things as needed. But then the entire transaction doesn't need to be as strict as a serializable transaction. Gives us essentially the same outcome though. So the benefits are just gives you finer control, and you don't have to change the isolation level. You usually don't want to mess with that. The disadvantages are it's just not directly supported in LINQ. So for our purposes, if using LINQ, the best option is use a serializable transaction. There are better ways to do this in LINQ, but it starts to kind of get beyond the scope of this class. This is a databases class, not a LINQ class, so we won't really go into that. It is capable of doing it in a better way, though. Just don't want to spend as much time as it would take to get into it. Okay? Any questions? All right. So, totally switching gears now. On the very first day of class, first and second day of class, when talking about the relational model, I talked about things like, let's say you want to select a bunch of information out of some table based on a person's name. And then another time you want to select a bunch of information from a table based on a person's age. How do you efficiently support both of those kinds of queries, right? If the table was sorted on name, great, you can efficiently find people based on name. If it's sorted on age, you can efficiently find people sorted on age. But it can only be one or the other. But we can add, so this is where I've talked about indexes. This is where indexes come in. So we're going to actually start talking about how can we use them, how do they work, what do they do. I will use the form of the word indexes, not indices. They are both correct. For some reason in my mind, indices means, in terms of computer science, indices means multiple locations in a list or array. I will just use indexes to make it more clear, like an index in terms of a database. It's not a location in a list or an array. Index in this sense is more like the index in the back of a book. It's additional information about the rest of the information. It's meta information. It tells you how to quickly use or access the rest of the information. Okay, before we do get into that though, let's take our 5-minute break. It's a good stopping point. It's different from any other program. What are the challenges? The biggest difference is that you're dealing with massive amounts of data. And then you also, its intention is to be very just a general purpose storage engine. So that means it also cannot predict how you're going to access that data, in what order. So those are basically the two challenges that we need to deal with. A DBMS is just a program, though. Like any other program, that means it's running on the same hardware that any other program is running on. There's a processor, there's some RAM, there's a disk. So it has to deal with the realities of that hardware. We know from writing, we know from optimizing other programs that it's best to try to keep things as close to cache as possible. We can reorder computations to make them more cache friendly. A DBMS is going to have the same problems, except the massive quantity of data is kind of going to move that problem closer to disk rather than closer to cache. So I've shown this before. This is a picture of a fairly modern processor. And what I want to take away from this is the massive amount of resources dedicated to storage of data. The cache, the memory controller, the I/O stuff, storage and movement of data. The actual computation part is somewhere within each of those cores, but still tiny. Let me fix these lights again, sorry. Can't see me as well, but maybe see the projector better. And here's the memory pyramid. The closer you are to a register, the faster you are. The further you are from a register, the slower you are. So registers are super fast, 0 cycles to access them. Cache, L1 cache is pretty fast, but small. L2, a little slower, but bigger. And that's basically the trend as we go down this pyramid. So, you've all seen this before. It's not a new idea, but basically the hardware is there to try to avoid the cost of moving data. They make this big hierarchy of it, and you as a programmer can write your code in a way that takes advantage of this hardware. But it's all there. Most of the stuff in a computer system is about moving data, not actually processing that data. There's an interesting barrier here, though, on this pyramid, right after DRAM. Everything up until that point is what's called volatile, meaning when it loses power, it loses data. If you turn the computer off, everything in RAM is gone, everything in the caches are gone. It is not a permanent storage device. So if you need permanent storage, obviously you need to store it somewhere beyond RAM, such as the disk. So all of this stuff is not going to work for a database system. It'll use it while it's running, but if it makes some changes, what it thinks are permanent changes, they are not permanent until they are written to disk. Power could be lost at any time, and then that data is lost. Okay, so this is all kind of about performance, speed, and robustness, volatility. Here is a plot of where is energy spent, like actual joules, physical energy. So look at there over on the very far right, 2.6% of the energy spent in some program was for actual computation, things like multiplies and adds. Everything else, accessing the L2 and moving data from the L2 to the L1, accessing the L1, DRAM, everything like that, is taking up the rest of the energy. And why does this matter? Why do we care about energy? Like, your laptop is not really gonna. You're not gonna see your computer anywhere on your power bill. Not really. It costs you like $1 or $2 a month. In a data center, though, a data center that has thousands of machines always doing something, energy is actually one of the primary costs of running a data center, like monetary costs. And when I say energy, I mean actually like their power bill from whatever power company they use. A lot of their money just goes to paying that power bill. Then, so this is the energy spent in just running the computer. The more energy you spend running the computer, the more energy you have to spend cooling the computer down. So more energy spent here means more energy spent dissipating that energy, and power bill goes up even more. It is actually a big concern in databases. You never really think about it as users of computers, but I guarantee Google is thinking about this. Okay, so all of this stuff is even more interesting and more of a problem when dealing with a DBMS rather than just some little program running on your laptop. The vast quantity of data basically takes the whole problem and shifts it further away from the processor and out into the slower, more expensive, more energy cost, or more energy consuming pieces of hardware. Okay, so the DBMS is a program. I run some SQL query, select whatever from wherever. Where's the data stored? How is it organized? How do we decide which parts of it to retrieve? The most naive thing is retrieve the entire database and then run some filter in the processor. Okay. So where do we put data? In DRAM, like a server machine does probably have a lot of DRAM, like 128 gigs maybe. Even that is not enough. The data we're dealing with is much bigger than that. Even if it was big enough, the bigger problem is that it's volatile. If power goes out, you lose the data. So we store it on disk. Yes, it's big. Yes, it's non-volatile. But isn't it too slow? Like anytime we have to run a select or insert, we have to go all the way to disk. Yeah, but we have no choice. We have to go to disk because of the nature of a database system. So our goal will be to accept that fact and figure out how we can mitigate the problem by understanding how a disk works. And then what happens is the DRAM on the machine now starts to look more like a cache. The caches are still there and they're still doing stuff, but the size of the data we're dealing with is so big that DRAM is really more like, now your goal is not really to keep everything in cache, your goal is to keep as much as you can in DRAM while the program is running. So we have to figure out what we can do about this. Let's talk a little bit about how disks work. So this is a magnetic disk hard drive. There are other forms. There are solid-state hard drives. You might be thinking that these are going away or have already gone away. They haven't, especially not in data centers. They're cheaper. They're more reliable. Data centers still absolutely use magnetic disk storage. So how does this work? It's kind of like a record player, if that analogy even works. But the record player, you have a tiny little needle sitting on some disk of the record, and the record spins, and as it spins, it conveys information through the needle by essentially bumping it up and down. Kind of the same idea with a magnetic disk. You have the platter. The platter contains many tracks. This name comes from like records. There are tracks in a record. And then you have the head, which is actually going to read the data. But instead of conveying information by bumping a needle up and down, the needle, or the head, is not actually touching the disk. It's just very close to it. And the disk is made out of a magnetic material that can be where you can easily change the polarity of the field for tiny little individual spots within the track. So switching polarity is switching bits. And then the head is basically an electromagnet, and as this track is spinning around under the head, the change in the magnetic field induces current in the electromagnet. And that's how you read bits. Okay, so each of these tracks and like regions on the disk, around the disk, are divided into what they call sectors. That's basically just like the smallest unit of data that a disk likes to work with. So on my track here, I have like a yellow, red, green, and blue sector on some track, and then there will be a bunch of tracks and even multiple platters. This is showing one platter. They actually stack platters on top of each other. Okay, so how does this work? To read some data, first we have to move the head to the right track. So just pick whatever point on the radius of the disk, rotate the head a certain angle to get there. Then, so that's called seek. Then we have to wait for the platter to spin around whatever sector we're looking for. We have to wait for it to be under the head. So this disk is just constantly spinning. Whenever you decide to read, you might get unlucky, and whenever you decide to read, the sector you're looking for might be on the opposite side of the platter. So you have to wait a full half rotation. Or even worse, it might be right after where the head is, and you have to wait basically a full rotation. Then, as that sector spins under the head, it induces current. So you have to wait until the full sector has passed the head. And then you're getting current out of it, so you're getting bits out of it. Okay, so this is a mechanical device. It actually has moving parts where computers are used to. I say used to. A computer's not actually a person, but usually they're dealing with speed of light sort of things. The electrons flowing through a wire is almost the speed of light. Now we're dealing with an actually just spinning disk and moving the head around, like way slower than speed of light. That's what makes disks slow, essentially, is the fact that they are a mechanical device. To give just some numbers, the average seek time, moving the head to the right track, is about 4 milliseconds. The average rotation time, also about 4 milliseconds. They can happen concurrently, but kind of in the worst case, you're dealing with several milliseconds. That doesn't sound like a lot, but a millisecond, how many cycles is several milliseconds? Depends on the clock rate, but it's a lot. 4 gigahertz processor is 1/4 of a nanosecond per cycle. And then you're dealing with multiple milliseconds. That's like an eternity to wait for your data. So how do we fix this? We can't fix it because physics. The way to fix it would be to somehow figure out how to store this data in transistors instead of on a magnetic disk. But we can't. So we can't really eliminate the latency, but we can be aware of it and we can work around it. You have to pay the cost of seeking and rotating. So once you have paid that high cost, you read a lot of data at a time. So that the theory is spatial locality. If you read 1 byte off the disk, you're probably going to read several consecutive bytes at some time in the future. So accessing a disk is definitely not on the byte granularity. It's much bigger. The OS does this for you, and the disk does this for you as much as possible. Like if you open a file and try to read 1 byte, the OS is actually going to read more like 4096 bytes off of the disk.
So if I'm wanting to build a database, or if I'm wanting to manage a big database center, generally do they buy a whole bunch of disk drives, or do they buy buy a whole bunch of consumer discs, or are there like, is there a market for like just like making big ass like industrial discs?
So, is there a difference between a consumer disk and a data center disk? Kind of. Some data centers, it depends on the data center. Some of them do actually just use like a whole bunch of the same hard drive you would buy off Newegg and put in your computer. There are more expensive disks that are more robust, that spin faster, but then you have to decide, is that cost worth it? Buying the more expensive disk, is it actually going to pay off? For some data centers it does, for some it doesn't. Some data centers just accept the failure rate. They make sure the data is replicated on lots of different disks, and there are actually technicians in there replacing multiple hard drives every day because they have so many hard drives that there are multiple failing every day. Some of them use fancier disks that don't fail as often, but so to answer your question, yes and no. There are expensive hard drives that you could buy, but you probably don't need to buy for your purposes. Why don't they use SSDs? Two reasons. One is cost, one is failure rate. SSDs have a higher failure rate than magnetic disks. And in fact, their failure rate is like directly tied to how many reads and writes you perform. Same thing is kind of true for disks, but they tend to last longer. Okay, so the OS tries to help you by reading a lot of data at a time. You can hurt yourself by randomly jumping around within a bunch of files or within one file. So you kind of have to be aware of this. The OS has to be aware of this. Disk has to be aware of this. But basically, the goal is to amortize the extreme cost of accessing data from a disk. Amortize means to spread out the cost. So what actually happens is the OS will read 8 disk sectors at a time, which corresponds to one page. Page being like a virtual memory page, 4096 bytes. So it turns out the granularity, the size of an OS page is related to how much data it likes to read off of disk. It's also related to the physical structure of DRAM, which is not important for today, but interesting stuff. So whatever program you're writing, if you know that it's going to be disk I/O heavy, you should try to write it in such a way that you do as much within one page at a time as you can before going to the next page, or like jumping around between pages. Okay, that's your basic goal. If you have to access the disk, do it in a way that you're going to get use out of the rest of those 4096 bytes that were read from the disk. Okay, so in summary, a database, the size of data a database is dealing with is much, much greater than memory size. So our problem becomes keep as much in RAM as possible rather than keep as much in cache as possible. We have to use the disk. We know we're going to go to the disk, so do it in a smart way. Okay, so let's just kind of look at some very simple examples where we have to pretend that it's a giant database, but I can't put a giant database on a slide. So what we're going to do instead is pretend that every row in these tables occupies a full page. So either pretend that a page is tiny or pretend that a row is gigantic, just to make this example work. So I have basically classes and departments. There's a foreign key between them, so the department is a foreign key in the classes table pointing to one of those departments, saying like what the location is, how many students in that department. It's a kind of variation on the LMS. So let's look at a query. Select department and name from classes. So for this query, I'm only looking at the bottom table, just classes, where num greater than 3,000. So this table up here is the result. This is what this query will return. So software engineering and statistics are the class num greater than 3,000. So the question is, how many pages will be accessed for this query? And this is basically the performance metric on a query. It's not like how many records do we have to look at. It's, the most important thing is how many disk pages do we have to load to perform this query. And remember, in this example, every row is 1 page. So basically the answer is 4. We don't know where those 3,000 level classes are within the table. They happen to be both at the end, but we don't know that. These are not sorted based on class number. So we have to do a linear scan through the entire table to find all of the 3,000 level classes. 4 pages accessed. Okay. What if, though, this table was sorted on class number? We could do something like a binary search. We could do something like assume that the 3,000 level classes are near the end, so start our linear scan at the end. Just to make it easy, let's do that. Let's just scan starting from the end and go down until we see something that's not a 3,000 level class. So this time we only had to access 3 pages, which is better. Not a ton better, but you have to imagine the example is bigger, right? We could go from like n pages down to n over 50 pages or something. Way better. The key there was I took advantage of knowing the order of the data. Okay, here's another one. So classes is still sorted on num, but now my query is select name where department is CS. Okay, how many pages? Yeah, 4. We don't. The being ordered by num does not help us with this query. We have to do a linear scan. Okay, now bringing back in the other table, because we're going to do a join. Select building from departments, natural join classes where name equals stats. So well, this kind of depends on how the engine executes the query. Here's the table we're going to get. LCB is the building where the stats class is held. But how did we find that? Does the engine do the join first, then the filter? Let's look at that. If it did the join first, you basically have to look at every single page. It's a cross product. It is a natural join, but in order to figure out the natural join, in theory, so database engines are smarter than this. This is like the worst case. Look at every single page. What if we filter first? We know we only care about this stats class. So what if we somehow eliminate these 3 rows and just find the stats class? Assuming we don't know anything about the order, that's still 4 pages. But then we can take that key, the key math, use that as the primary key in the departments table. And let's assume that the departments table is ordered by department. Now I can quickly find, using that key, I can quickly find that record to find the building. So I had 4 to do the filter plus 1 to do the join. So that's a lot better than 7. And this could be even better if the classes table was ordered based on class name. We had to do 4 because it wasn't, but we could do fewer if it was. So what I'm getting at is knowing something about the ordering of the data lets us access fewer pages on the disk. So, okay, so having sorted data is good. Without sorted data, it's order n, access every row. You might be able to stop early, but still on average it's n over 2, big O n. So how do we fix this? One possible solution: make multiple copies of the data, each sorted on whatever query you might want to run. So one sorted on number, one sorted on department, one sorted on name. It would It would, in theory, make it faster. But no, that's way too much. We're already dealing with too much data. Having multiple copies of your entire database for different queries, no, not going to happen. So another solution. Sort the database based on whatever the query is you want to run. The sort operation requires touching every single page. Can't get around that. But if you pay that high cost once, then you can do those queries quickly. But that only works for one kind of query. What about if I want to select based on some other column? So neither of those really work. One of them makes one kind of query fast. One of them makes all queries fast, but blows up the size of the data too much. So what we do is we keep just one copy of the data in whatever order, and we make auxiliary data structures called indexes. So these indexes, all they are is you build a data structure on one specific key, one column, or multiple columns, the one subset of the data, and then all it holds is that key plus a pointer into the actual table. So here I've made a num index and a name index. So the num index is ordered by the class number, and name index is ordered by class name. And notice they have pointers kind of just going all over the place into the actual data where the full row is stored. I've drawn these indexes as tables. Think of them as tables for now, it's fine, or just think of them as an ordered array. They're not actually arrays. We'll get to the actual data structure next time. It's a tree. It's not quite a binary search tree, but kind of the same idea. Okay, so so now if we want to access some data, we first go to the index. Say we're looking for the class with number 1410. So instead of starting in the actual data, we go to the num index. We have to find the 1410 pointer into the actual record. So doesn't this mean now that we have to access more data? Like instead of just accessing the main table, we're now accessing another table? Yes, it does. But it reduces the algorithmic complexity. So accessing just the main table with no kind of order is order n. Using an index, we get logarithmic search through the index itself using something like binary search, and then +1 to go get the actual row out of the other table. So number of pages touched is, although we're looking at two different tables, the total number of pages loaded off of disk is way, way smaller, logarithmic versus linear.
We're not actually copying these columns over and over again, right? To make these different indexes.
So are we actually copying these columns over and over again? No, you copy them once when you create the index. And then the index itself is actually stored on the disk somewhere as well. Whenever the main data changes, the index has to change as well, because you might be adding new keys, and the index needs to track those new keys.
Should the O value not be simplified to just all of log n?
Yes, so I only have the actual log part inside of the big O. The +1 is just saying, yes, once you have logarithmically found the key you're looking for, that's just saying what you actually have found is not the row, you've found a pointer to the row. Then you do actually have to go load another page from disk. But you're right, if this whole thing was big O, then you ignore that +1 constant.
How long does it take to make that index?
How long does it take to make the index table? Depends totally on the size of the table. Usually you make the index before you have added any info to the table, so the index is just updated as rows are inserted. You can make an index after the fact, and if you have a gigantic table, then it might take a while to build the index.
Cool. So the cost is not, doesn't include making the table, it's just using that.
Right, the cost of doing a lookup does not include creating the index. The index is already there.
And does the index need to be a primary?
Does the index need to be a primary key? Kind of the other way around. The primary key always has an index, but you can make a secondary index on any other column. Okay, so another thing about this is, it looks like we've made the problem worse. We've added more data that we now need to load. But we've gained huge wins in the algorithmic department, complexity department. And it's not as bad as it looks because these index tables are actually very small. All they hold is whatever key the index was built on plus a pointer to the main table. And in fact, I won't draw them this way today, but it turns out you don't even actually need to save every key in the index table due to the way that data structure works. So these index tables are very compact, very small. It's not as bad as it looks adding all this extra data.
Why not just add an index for every column?
So why not just add an index for every column? So although they are small, they are not zero. And updating these indexes is a performance issue. Every time I change the main table, I have to change every index table. Okay, so let's do an example. Just as before, main records are 1 page per row. But since these index tables are ordered and since they're small, we'll assume that we can search the entire index in 1 page access. And that is actually fairly realistic. It won't be always 1. It'll be like 1 or 3 or 5, some small number. So here's the original example we did where I was looking for classes with num greater than 3,000. And without any ordering, we had to access 4 pages with an index. So now I have an auxiliary index over here. And as I said in the problem, we can search the entire index table in only 1 page. Ignore that. We can do a binary search or whatever to find 3070 and 3500, search the entire index in 1 page. Then we take those 2 pointers and go load the full rows out of the real table, and pretending that those are an entire page each. But the total is 3 pages. So we've done better. And this problem is too small to make it way better. It's 4 versus 3. Really, though, it's order n versus order log n. Okay, here's the one with the natural join.
Is it possible to partition the index like data structure you created on that last slide where you're trying to point to, say maybe you wanted to index on department and it says I have, CS is pointing to 2 numbers. You have a partition on that index. It's like I want all thousands in this part of it, all 3,000 classes in this part of that index.
So can you partition based on
So I guess the
1,000 versus 2,000s versus
Could
3,000s?
you change the data structure that the number index is pointing to put like a sub-index?
Can you make like a sub-index? Kind of. You can make a complex index. You can make multiple indexes. We'll get to that. Okay, here's the one with the natural join. Without indexes, say we get unlucky. We filter first. We get unlucky, have to access 4 pages. And then we do the natural join, not knowing anything about the order. We have to access 3 pages to do that natural join. So 7 total. Okay, now let's say I have an index on departments.department and classes.name. So I've added 2 indexes now. What this allows us to do is use the name index to first do the filter to find math or stats. So that's 1 page to search that index, plus 1 page to pull out the full record to get the department number. Then I use that department number as a key into the other index, the department's index, and I search for that all within 1 page. So we're up to 3 pages total. I find the pointer I'm looking for, and then go load the full page out of the departments to find the building. So that was four pages total versus 7. It involved 2 indexes, and it involved 2 actual tables. So this data was spread across a lot of different places, but the number of pages we had to visit was still smaller. Okay, so what does this mean for us as like users of SQL? Every table has a primary index because every table has a primary key. It automatically builds an index on that column or columns. And so this is actually special. This is called the primary index. But we can also add secondary indexes however we want. You can choose which columns. You can put an index around multiple columns, or you can put multiple indexes on separate columns. And it's up to you to decide which columns need them and which don't. And you can even decide in some DBMSs, you can decide how the index actually works. So there are kind of different data structures you can pick based on the kind of query you're going to be doing. And so all we do is create index and then pass it in a column list. And that will build the data structure on whatever columns you specify. Okay, so how do we pick? Don't just put them on every single column, because not only would that be costly in terms of you now have to update a bunch of indexes, this would actually be more indexes than you think, because you can have multiple columns in an index. So you would have to build an index on every possible combination of columns if you wanted to do that. Don't do that. Instead, think about the kinds of queries that you're going to be doing on this table. Like, if you're never filtering based on whatever column, then you don't need an index on that column. And unlike the primary key, there's no need for whatever column to have uniqueness. You could have a whole bunch of, say, 3500s, number 3500, in whatever index, and it's fine. Okay, so going all the way back to this library example, we're going to look at where do we need indexes for certain kinds of queries. So let's say, so I want to know what are the appropriate indexes if my common query is get all of the books checked out by a certain person by name. So we know the person by name and we want to get all the books checked out. What we already know is that cardinum is primary key in patrons and serial is primary key in checked out. So we have indexes there. I want to know what additional secondary indexes might we need. So let's actually do this. It'll be probably fast. Take 1 minute with people around you. Tell me what additional indexes you would add to make this query fast. Okay. Hope that was about a minute. So, who wants to offer an answer?
Since you're just going to read through every row of patrons anyway, it's only beneficial to put an index on checked out as cardinum.
So, only beneficial for checked out's card num. So why not? So you said, since you're going to read through every row of patrons anyway, why?
Because if I was to start with, I'm going to have to start with Joe, and I already know Joe is card num 1. Then
How do you know Joe is card num 1?
Because it's linked on the same tuple.
But all you start with is the string Joe.
Are you saying that you're going to have a where clause that says I'm looking for Joe?
Yep.
Okay, then yeah, put an index on name as well.
Okay.
I
So
thought you were just listing every name with
I see.
every.
No. So get books checked out by whoever the patron's name is. It's maybe a little unclear, but so the first thing what we have is a person's name. So we need an index on name. That's going to make that look up fast. And we additionally need one on checkedout.cardnum, because given the name we're going to have a card num, we can use that to find the book. But the primary index doesn't help. Primary index is on serial. Okay. Here's another one. We won't actually do this as an exercise, but let's think about this for a second. So this is a different table now. This is back to like the classes. Select name from classes where department is CS and num is 1030. So there might be multiple 1030s. In fact, there are. There's a math 1030 and a CS 1030. I want the CS 1030. We don't know anything about the primary key, so ignore that. What secondary key or maybe keys would help with this query? The obvious thing to try would be maybe we'll put one index on department and one index on num. That turns out to not really help us. So if I have one index on department, okay, so I can quickly find all of the CS rows in here. But then I have a whole bunch of numbers that I have to look through. And I have to just look through all of them to compare to 1030. Having another index on num, even though I could quickly find the 1030, I could not quickly find the 1030 that is also the CS. So that index actually won't really help. It'll help a little bit. It'll first pare it down to only the CS classes, but then it's still a linear scan through all of the CS classes. So there is an index that will help with this. It turns out we actually can just put two columns into the same index. And what it does is literally just appends the first column, appends the second column to the first column, and that becomes the key. So in this case, I actually have a string and a number. It actually just takes like the string version of that number and appends it to the string. So look at my keys now. They are CS 1030, CS 3500, and so on. Now I can just look through that one index for a string CS 1030, and there's only one of them. It gets me immediately to the row I want. What about, so assuming I have this index, will this index help for this query? Select name from classes where department equals CS. Does this index help? It's more than just names, but can I still use it for just names? Turns out, yes. All you do is, so whatever string I'm looking for, I know that it's CS, so all I do is look at just the first two characters of the key in this complex index. And that is still sorted by class, by department name. Question?
So if you have like a gate type or something, as part of that, multiple keys, just convert the data into a string, then
Yep.
look up that string.
Yep. Okay, what about this query? Same index. Does it help for this query? Select name from classes where num equals 1030. Hold on. So say that again. Okay, so same logic applies. You know the number is in that key somewhere. So maybe just go and look at the part that is the number. So a couple problems is first, you don't know that the first part of the key, you don't know how many characters that's going to be, so you don't know where the number starts. But an even bigger problem is, so let's say we're looking for 1030. Can we quickly find the 1030? Yeah, we have two 1030s in here that are out of order relative to each other. So this index is sorted primarily by department and only secondarily by number. So it turns out this index does not actually help if I'm only searching by number. So the order of these multi-column indexes matters. This index, department comma num, is not the same as num comma department. Both of them could be useful depending on what kinds of queries you're doing.
Is there no write function in MySQL that just takes you pass it in the string you want, it just goes the last 4 digits? So it starts from the right of your string and goes.
Oh, so if you used like a substring operator to just look at the last 4 digits, okay, you're right. That does solve the we don't know where it is within the string.
The first 2 over there, like you use a let function that puts the first 2. Or
You don't need to do that. You don't actually need if you do this query on this index, it automatically works. If you do this query on this index, it doesn't help you at all.
So it automatically compares to the first
Yes.
whatever string it is.
Yep. Okay. Out of time for today. See you next time.